Hello everyone. So today we are going to discuss about Maxwell's equations, one of the profound equations you can find in physics, electronics and communications. So in our daily life we are using mobiles, laptops and Wi-Fi routers, whatnot. Each and every equipment is carrying electromagnetic waves. So how these electromagnetic waves are generated and how they are propagated. So these Maxwell equations will answer you. So going into the topic, and God said, del cross E is minus dou B by dou T, del cross H is Z plus dou D by dou T, del dot B is 0 and del dot D is rho B, and then there was light. That means if you have all these four equations, you can generate electromagnetic waves. You can allow them to propagate to longer distance. How? We will go into the topic. So coming to the first Maxwell's equation, which is the Gauss law. The surface integral of electric field intensity is nothing but some factor times the charge enclosed by it. I'm not going in details about what is the surface integral, how you can change the surface integral from how you can change the surface integral to um, the point form del dot D. Okay, I'm not going into the derivation, but I will give you a pictorial representation of each and every equation here. If you consider a charge Q, then you will be having some electric flux coming out of it, and if you want to mathematically find what is the electric flux coming out of this charge Q, you can assume a surface around it simply. This is the Gaussian surface, I can say. And if you integrate the each and every point on this surface, if you integrate the electric flux on each and every point on the surface, and if you sum up all those points, you simply get Q. So that's what the equation says. The electric flux psi, which is coming from the surface, closed surface, okay, is nothing but the charge enclosed by this surface. And if you change into the point form, you can tell it del dot D is nothing but rho V. Del dot T is nothing but the divergence of electric flux density. That means the divergence, if you see, um, if you open a gas valve of a cylinder, the gas starts diffusing into your room. That is nothing but divergence. The similar way, the electric flux will diverge from the electric charge. If it is coming in the opposite direction, then it is called as convergence or negative divergence. If you have a positive charge, you will be having a divergent field. If you have a negative charge, you will be having convergent field. Here I considered a positive charge, so I am having a diverging field. So if you see the Maxwell equations, they are linking the electric flux and magnetic flux to their sources. I'll show you the magnetic field now. So if you see here, the electric flux coming out of a surface is simply related to its source, which is inside the surface. Okay. Coming to the next equation, del dot B is equal to 0, or the closed surface integral of magnetic flux density is 0. Here you can understand, as I said before, if the flux is going out, it is called divergence. If it is coming inside, then it is negative divergence. If you are having both going out and coming inside, then the net flux density will be 0. If you are having n number of flux lines going out and n number of flux lines coming inside, then the net flux n minus n is always equal to 0. This is the case where it will happen. If you take a bar magnet and if you cut into smaller and smaller pieces, you will end up with a magnet with a north pole and a south pole. You will not get a magnet with only north pole or only with south pole. That is why if you consider a surface around this magnet, then you can have a magnetic field of lines that are emerging from north pole to south pole, if you see, like this. And if you see, number of lines emerging out of this surface are always equal to the number of lines coming into this surface. If you have single north pole, then you will have only um, the flux which is going out. That is, then you will be having divergence. And if you are having only south pole, then you are having only convergence, negative divergence. But here, in this universe, you cannot find that. You can only have only a bar magnet with north and south pole. Now you might have thinking about why we couldn't find the north pole and south pole. That is a different concept. I will also come with that concept. Why we don't have magnetic monopoles in our universe. And why, if you consider a charge of Q, why electric flux is coming out? Okay, if it is coming out, it will be diverging or converging, which is told by Maxwell. But why the electric flux is coming out of a charge? Why it is emanating? What is there inside this electron? What is there inside this charge? That is a different topic. I will also come with that topic. But if you assume that something is coming out of this charge, how it will be? That was said by Maxwell. So these two equations which we saw just now, del dot D equal to rho v and del dot B equal to 0. These two equations are connecting the magnetic and electric flux to their respective charges. And here you cannot have a magnetic monopole, still you can have closed loop of magnetic lines. Okay. Next, so these two equations uh, told us what is the relation between the flux or the field lines and their respective source. And coming to equations will tell you how they will propagate. I will tell you how. So the third equation is nothing but the Faraday's law. Long back Faraday discovered this law, which tells that if you have a change in magnetic field, okay, and I said before, for generating this magnetic field, you don't need any magnetic monopole. You need something. I will tell you later what you need. So let us assume that you are having a changing magnetic uh, flux density B. If you are having a magnetic flux density, changing magnetic flux density, and around this changing magnetic flux density, if I have a conductor around this changing magnetic flux density, I am having a conductor. You can have an electric field also. That is the magic in this. That means magnetic field and electric fields are no more separate. They are interlinked. You cannot say electric field. You cannot say simply magnetic field. Of course, you are having a static electric field and static magnetic field, then it's okay. But if these two are varying, combined you can call them as electromagnetism, electromagnetic fields. Because if you are having a changing magnetic field, you will always have a change in electric field or a rotation of electric field around this magnetic field in perpendicular direction, if you see here. So this was a very good discovery made by Faraday. And if you see the line integral of electric field is nothing but, if you assume a surface around this line integral, if you assume a surface, if you assume a surface which is bounded by this line integral, which is bounded by this line integral. And if magnetic field is piercing through that surface, and if you integrate the magnetic flux at each and every point on that surface, you simply get the electric field which is rotating around this contour. And in point form, I can tell the curl of E. Curl is nothing but the rotation of E. That means the electric field tends to rotate. If it is going like this, then the magnetic field which is changing, it allows it drags that electric field in this manner. Then the electric field will rotate. That is the great discovery. It's a mind-boggling discovery. So here, the third Maxwell equation, if I say, is telling you is connecting between the E and B. It's connecting between the electric field and magnetic field. And as I said before, how can you get this magnetic flux density? Because electric field anyway you can get with a point charge. And this Faraday's law states that if there is a change in magnetic flux density, how do you generate this change in magnetic flux density? You can have a varying magnetic flux, or you can also have a current carrying conductor. This was the fourth Maxwell's equation defined by Maxwell, nothing but Ampere's law, which states that if you have a current carrying conductor, if you are having a long current carrying conductor, and then you will be having a magnetic field around this conductor. And that was also a great discovery, if you say. Then the people were playing with conductors, magnetic compass, everything. So this was a very good discovery. There will be a rotating magnetic field around this conductor. So the line integral of this magnetic field intensity, as I said before, if you assume a surface bounded by a line, and if there is a conductor which is piercing through this surface, and if you integrate all the current which is passing through this surface, you simply get the magnetic field intensity rotating around this curve. So in the point form, I can say del cross H equal to Z. Now, so we all saw all the four equations of Maxwell, but there is some inconsistency in this Ampere's law. It is telling that if you are having a current carrying conductor, only then you can have the magnetic field intensity around it. But if you take a capacitor, what about it? Because capacitor is nothing but it is having two charge carrying plates and the two conductors. You can see here. And if you allow the current, varying current, AC current, to pass through this capacitor, current will flow through the capacitor, even though there is no conducting medium between these two plates. And if you have a magnetic compass, if you take that magnetic compass and you put just beside these two plates, still you will get a magnetic deflection. That means to get a magnetic flux, change in magnetic flux, you no need to have only the current. Something must be there. Because if you put the magnetic compass near the current carrying conductor, you can simply tell that, okay, because of this current, as according to Ampere's law, there will be some rotating magnetic field. But what about capacitor? Still, if you can see, the magnetic needle will deflect near to this capacitor plates. So apart from the current, something is there. The same idea emerged into a new form of Ampere's law. So Maxwell took a page from Faraday, and he thought that there will be Faraday told that if there is a change in magnetic field, then we'll be having some electric field around it. Maxwell thought in the other way. What if we have a change in electric field? Can we generate change in magnetic field? Oh, then there would have been some electric field between these two plates which is changing, and because of which it is producing a change in magnetic field which is causing the needle to deflect. Okay, if this is correct, then how to find the change in electric field between these two plates? It's very simple. You have Gauss law. If you have a charge, if you want to find the electric field emerging out of it, you can consider a surface around it. Here, the capacitor plate itself is charged because of the current flowing into it. But at the plate, at this boundary, the conducting current is zero because there is no conductor between these two plates. Still, the plate was charged, and if it is charged, according to Gauss law, there should be some electric flux coming out of it. Then, from Gauss law, here you can see the closed surface integral of electric field, sorry, is nothing but some factor times epsilon naught times q. The q is the q is nothing but the charge on the capacitor plate. Now, here I'm not having a closed surface. If you see, I just assumed a surface around that which covers the capacitor plate. I'm not having a whole sphere. So, if I remove that closed surface symbol on the integral, and I want to know the change in electric field, because only then, according to Maxwell, we'll be having change in magnetic field which reflects the needle. So I took the derivative. If you see the right hand side, dq by dt is nothing but the current carrying in the conductor. So that means the current itself, see what is the magic here? The current itself which is flowing through the conductor of the capacitor plate, that current itself is changing into a change in electric field. Actually speaking, it is not electric field. It is not the change in electric field because it is nothing. The change in double integral of epsilon naught times E dot dA, and that is nothing but the change in double integral of electric field intensity, electric flux density. Sorry. So D is electric flux density, and if you integrate the D, what you will get? You will get electric flux. So the current is changing into the electric flux. Okay. So then Maxwell appended the Ampere's law. Instead of putting simple I, he included the change in electric flux. If you see, the current carrying conductor will not have simply a current I. There will be some electric change in electric flux across that surface around which the magnetic field is rotating. Because if it is not there, then the capacitor wouldn't have shown the deflection in magnetic needle. So that means you have to consider both the conducted current and the change in electric flux. Maxwell called this as the displacement current. So simply if I say del cross H is nothing but J plus dou d by dou t, and this dou d by dou t is nothing but displacement current density. That means this current doesn't need any conductive medium. If you have a non-conductive medium, then you can have this dou d by dou t. That means even though you don't have a current carrying conductor and you are having a change in magnetic field, you still have a change in electric flux. Faraday told that if you have a current carrying conductor and across that if you have a change in magnetic field, then you will be having a voltage you can measure in this conductor, and you will have electric field, change in electric field across this. But even though you don't have a conductor, still you can have a change in electric flux according to modified Ampere's law. This was the great astonishing amendment I can say, that had been done to Ampere's law by Maxwell. So now you all have all the four Maxwell equations. Now how, so first two equations told us how the electric field and magnetic field will generate from their sources. Now last two equations, the modified Ampere's law and Faraday's law. What these two equations will tell you about the propagation of electromagnetic wave. So okay, I'm having a charge, varying charge. So I want to generate electromagnetic waves. How can you generate electromagnetic waves? I will tell you now. Assume you are having a plain electric wave. That means you are having only electric field. Okay. So these are two waves I have shown. I will tell you why. And if you see, you can always find a rotation of electric field between 2 points. Any 2 points if you take. I have taken the maximum points. One is at um, positive maximum and one is at negative maximum. And if you see, at this point the electric field is in this direction, at this point the electric field is in downward direction. So you can have a rotation in electric field if you consider across this surface. Okay. Now, if you have a rotation in electric field, there must be a change in magnetic field across this surface, right? This is according to Faraday's law. Because you are having electric field, change in electric field, you must have magnetic field across the surface but in perpendicular direction, because according to Faraday's law, magnetic field and electric field are 90 degrees apart. And if you see here, since we have considered maximas, that means you are having a maximum rotation at these 2 points. So at exactly center of this surface, you will have a maximum magnetic field. You can see a long arrow for magnetic field only at the center of this surface. That means there is a 90 degrees phase between the electric field and the magnetic field. And if I say, I can also have a magnetic field at the later stage. And again, if you consider a closed surface around this magnetic field, there will be a circulation of magnetic field. And as I said before, if you have a circulation of magnetic field, the cause of it need not be only a current carrying conductor. It can also have a change in electric flux, which are these blue lines you are seeing. So if you are having a circulation of magnetic field here, the orange lines, if you consider a circulation, you simply have a change in electric flux across that surface. That was a very good idea brought up by Maxwell. Because in space, you cannot have electric conductors. If you are having a change in magnetic field, as I said now, you cannot have a current carrying conductor as for it to cause. You simply have a change in electric flux. If you have electric flux, then you can have a change in magnetic field. That means if Maxwell's wouldn't have brought up that idea, you simply think that okay, if here we are having a circulation of magnetic field, so we cannot have electric flux across that surface. But Maxwell added the term the displacement current density. So you are having the circulation between the magnetic lines here I have shown. Then you will be having the electric flux passing through that surface. You don't need any current carrying conductor to have that magnetic flux. So now, if you have electric flux, changing electric flux, then you can have a magnetic flux, change in magnetic flux, and that magnetic flux will again generate electric flux according to modified Ampere's law, and that again the change in magnetic flux will have a change in electric flux according to Faraday's law, and the electromagnetic wave will propagate like that. The magnetic field will create electric field will create magnetic field. These are self-creating fields. So finally, if you see the Maxwell equations, the first two equations will tell you the relation between the flux and their respective sources, and the last two equations will tell you how the electromagnetic wave will propagate, how these self-generating fields will generate. If you don't have that extra term founded by Maxwell, you cannot imagine an electromagnetic wave in space, because the change in magnetic field, you think that the change in magnetic field, if you have a change in magnetic field, you should have a current carrying conductor across the surface, but that need not be true. You can also have the change in electric flux. You no need to have a current carrying conductor. Alas, now I can generate electromagnetic waves in free space also, because I don't need any conductor. So this is the basic idea behind the generation of electromagnetic waves. Thank you. If you have any doubts, you can ask me in the comment box. Thank you all.